In this lesson, we're going to look at the Newton-Raphson method. The Newton-Raphson method is a numerical technique for finding roots of equations. Some equations we can't solve algebraically and find exact solutions, but we can see from the graphs that they do have roots. And we can find those roots using numerical techniques, and the Newton-Raphson method is one of these techniques. Using a method like this, we can find the root to as many decimal places as we need. The Newton-Raphson method utilizes the tangent to the curve at a particular approximation to a root to find the next approximation. It might be handy to have a picture to give us an idea of what we mean there. So we can see there's a root here. Now, we might take a first approximation to that root at a point like this, and we would call that first approximation x naught. Now, the curve is y equals f of x, so we can find this point by using x naught and substituting that into f of x. And that tells us that this point is x naught, f of x naught. And then we can find the tangent. The tangent cuts the axis here, so we would use that as the next approximation, and we would repeat that process. So like the other techniques that you've met, it's an iterative technique. Consider the tangent at xn, f of xn, so this is some distance along our iteration sequence. Y is going to be f dashed of xn, so that would be the gradient, and we know that the first differential is the gradient function, x plus a constant. To find c, f of xn is going to be equal to f dashed of xn, xn plus c. So we've just substituted in xn and f of xn as y and x. So c is going to be f of xn, take away f dashed xn, xn. And so our tangent is y is f dashed xn x plus, and that's the constant there, f of xn, take away f dashed xn, xn. The x-intercept of this tangent is xn plus 1. And of course, y is 0 because it's an x-intercept. So 0 is f dashed xn, xn plus 1, plus f of xn minus f dashed xn, xn. We can rearrange this, and if we continue to rearrange to get xn plus 1 as the subject of the formula, we end up here, and of course these f dashes will just cancel. And so we end up with the Newton-Raphson formula that xn plus 1 is xn, take away f of xn over f dashed of xn. And that's the formula we're going to be using when we're applying the Newton-Raphson method. When this method works, it tends to converge very quickly. It's a very efficient method. However, it can fail, which it tends to do quickly as well. When it fails, it tends to fail spectacularly. And it's sensitive to starting values. So for example, because it's based on a tangent, if you do it at a turning point, you're never going to get an x-intercept. So if we start at the turning point, the tangent will be horizontal, and so unless the turning point is actually a root, we never get an x-intercept. If the turning point is a root, the tangent is simply the x-axis, and that's no use either. Then we could look at a situation like this one here. We're starting to look between these two roots, but it's likely to go ahead and find this root over here. So where you start with Newton-Raphson can determine what exactly you find, and that's something you need to take care with.